Hello everyone. I wanted to use these last few lectures of the course to discuss about the application layer. We've discussed in detail about the lower layers, physical layer, DLL, network layer, transport layer. And the layer where we have most flexibility is the application layer. Okay, so we can pretty much do whatever we want over here. We are not restricted by the OS or anything like that. So what should we discuss about the application layer? There are so many applications out there, so many interesting things happening. And of course, this course is focused on networking. So we will look at just a few things which are very key and which you will come across quite often, when you use the internet. So one of the things I wanted to discuss first is peer-to-peer networks. So of course the internet wasn't designed for peer-to-peer networks, though they became quite popular, I would say in the late 90s, and they're still very popular today. So what exactly is a peer-to-peer network? Well, usually we are used to the client-server model, where there's a client who gets some service from the server. Okay, so the client is the server which does some duty or the other. You can think of a Google server, for example, maybe which does a search for us. Right? And that's the client server model. And this was the paradigm earlier on in the initial few decades of the internet. So how the peer-to-peer network differs from this is that in a peer-to-peer network you have peers. So these are various hosts which we will call peers, and these are equals. So they are it's not like here where the server has a particular role and the client is doing something else. The client is getting a service from the server. In a peer-to-peer network, all could be equally contributing to the service. Okay, and somebody might take the service from somebody else, and that same person might also give the service to somebody else. So they are all equals, and these are all connected to the internet, and they together form this peer-to-peer network. So how do these peers get together to form a network? That's something that we'll have to think about. How do they get to know about each other? That's what's called the bootstrapping. How do you start out the whole procedure? Right. So we'll have to talk about that. But then, what sort of service do they offer? And then how, of course, to perform that service. So as the internet was picking up in the 90s was the big boom of the internet. There was this craze, dot-com bubble was created because of that, and of course there was a dot-com crash around the 2000s, which you may be aware of. The whole stock market just collapsed very quickly. Right? Because there was a lot of hype about the internet, and they would say that internet is going to solve all our problems, and when people realized maybe that's not so true, then things collapsed. Okay, but even after the dot-com collapse, the internet did produce many new ideas. So things like Facebook and so on came up after the dot-com collapse. Right? So lots of things did. The internet has delivered, but maybe people didn't estimate the time taken for it to deliver whatever was promised. Anyway, so how did it come out and how did peer-to-peer networks start out? So in the 1990s, people thought, why don't I share digital content with the other people? Before the internet, there wasn't a very easy method of sharing digital information. There wasn't like a global internet people could connect to each other. Right? But with that, people thought, why don't I share? So suppose I have, let's say, a movie file or let's say just a music file. Why don't I just share it with my friends or in this peer-to-peer network? So the idea was, suppose this person has, let's say, a particular file. Okay, Michael Jackson, let's say, was a popular person, in those days, and still is. But so people might want to just upload a file of Michael Jackson, So somebody might say, I have a Michael Jackson file, and somebody may have another music file of some other artist. Right, so maybe they paid for it and they bought it, but then they want to help each other. So this guy says that I am willing to share my music with you, and I would like you to share your music with me, so that we sort of become friendly and share our information with each other. So that was the idea. We share this digital content so that everybody doesn't have to pay for it. Everybody doesn't have to buy the music. So this was the idea, and something called Napster came about. Napster was one of the first companies which originated this peer-to-peer idea. And this, essentially the service was this: I offer whatever files I have, and anybody else can download them, and anybody else who wants my files can also do that, and we sort of share with each other. So how did it work? So there were these different peers. Anybody could join the Napster network, and Napster was centralized. So the Napster, let's say, would have some sort of a server, and you could connect to the server. And let's say that these different people, these different peers could log in over here. Okay? And what information would you put here when you log in? Okay, so let's say this is A. So this has a particular IP address, and he might say that I have a certain set of files. Okay, so let's think how it might work. So A logs in, and A gives details of whatever files he has. So there could be an Napster application, let's say, where you can use to log in here, and you can sort of just share some file information about what you have. Okay. So what does the server record? So the server would have information like this. It would say that there is a particular file. There could be a file name, maybe the file name is a name of a song or something like that. And there would be the IP address of A. Right, so let's say this is file 1, and let's say B does the same, and B says that I have file 2. And this proceeds. So this server collects a lot of information about who has what files. So let's say that C wants to search for some files. He doesn't own some Pink Floyd file or something like that. So he just wants to search. He's heard that there is a school website called Napster. So he logs in. So C logs in to the server, to the Napster server, and he does a search. For some particular song, let's say, right? And this server has information about the various files, so it will do some sort of a keyword match, and it will suggest, that these are the files which potentially match the song name that you have given, and you can download it from these various other peers. Okay. So let's say that there is a match with file A, file 1, and there could be a match with several other files, and so this information is given to C. And now of course C can download the file from A. So this is a straightforward enough idea. Of course, only once things are built we realize that they are very simple. Right? So before Napster came out, people didn't think of these ideas of file sharing, or that there would be an easy way to do it. So Napster, of course, made big bucks because they were providing a service which lots of people wanted, and they were in the news all the time. But as you can expect it, the music industry didn't like this, because they were losing a lot of revenue. So somebody, let's say a music artist, or maybe the company, the recording company, they used to make so many millions selling their songs to different people, and now it was being sold, or not even sold, it was being given to others for free, and they were losing a lot of money. So they sued Napster, and Napster lost the case, right? Because obviously there was something illegal going on here. People were sharing files, and it wasn't. It was violating all sorts of rules. So Napster had to shut down. This happened around the late 90s. So why was it so easy to shut down Napster? Well, one of the drawbacks was that it was centralized. So whenever you have something centralized in the internet, it's very easy to target it. So first of all, from a fault tolerance point of view, it's a single point of failure. So what I mean is that if somebody takes down a server, then the full service is gone. And the server might be, let's say, one physical machine, or maybe a few physical machines with some particular IP address. So somebody brings down that server, then that's the end of the service. So as we'll see that now we have decentralized peer-to-peer systems which are much more robust. For example, the Bitcoin is built on a decentralized peer-to-peer network. So it's very hard for anybody to take down the service. Also, from a legal standpoint, it was easy to bring down. So the US government or some court can just tell Napster that you have to take down your server. It's illegal. And Napster is a company. It has people who are running it, the CEO, CTO, or whoever. And if the judge decides to take them down, then they have to obey. Right? So it was easy to take them down. Okay? And also, this wasn't so peer-to-peer. Ideally you would want a complete decentralized system without this server. Of course, it is sort of peer-to-peer in that C is downloading the file from A directly, right? Or B might download from C or something like that. And that's sort of the peer-to-peer system, but there is still the centralized point where they have to search for information. So if we can get rid of this, that would be even better. Okay. Next after Napster was Nutella, which became a very popular peer-to-peer system. So Nutella didn't have a centralized server like Napster. So the centralized server, we said, is essentially a single point of failure and a single point of attack if somebody wants to bring down the system. So let's suppose that we don't have a centralized system, but of course we would have to have some sort of connectivity between the various nodes. So let's say we had a graph like this, where A was connected to B, B was connected to D, D was connected, let's say, to C, C was connected to E, and so on. Right? So first of all, how do you set up such a network? And I mean, so maybe initially, let's say that this was the network. We didn't have A over here. So we need to first talk about the bootstrapping part. And suppose A wanted to join the network. So how would A do this? So first of all, A might know about some peers just in the application itself. So the Nutella application may have IPs of some other peers. Okay, so of course the application could just try those and see if they are alive or not. Okay, so this is one way to do bootstrapping. This is sort of a standard technique. And the second method is you don't have the IPs exactly of these nodes, but in the application, but maybe you have some website which you can contact and get that information. So this has to be done quite well in order to keep the system up and running, right? Because you don't want a node to start up and then it doesn't know how to join the peer-to-peer network. So let's suppose that B's IP address was there either in the application or it managed to get it from some website, and A joined the network this way. So this is how you would set up the network. But now how to search for a file? So suppose A wants to search for F. So F could be a set of keywords, let's say, which it wants to look up. Now there is no centralized server, so how is it going to do that? So you might want to think about it for a moment. Suppose you were designing this. So A wants to search for file F. So obviously he has to contact B because that's the only peer that it knows right now. But then what if B doesn't have the file? Then what happens? So the obvious idea that comes to mind that B will forward it to D and so on. And the question is, till when are we going to do this? You know, the brute force method would be to just broadcast a query message throughout the entire network and somehow send the results back to A. So suppose D has the file, it would send it back, but what if D didn't have it, right? I mean, are we going to broadcast to the entire network and then everybody contacts A? So that seems to be an overkill. So what we will do instead is a limited broadcast. So what is a limited broadcast? Well, you can broadcast the message but only limit the message to go, let's say, 2 hops away or 3 hops away. So how would we do that? Well, we would have something like a TTL, like we had an IP TTL, but here the TTL corresponds to this application layer. So if TTL is n and TTL is decremented at every hop, and if TTL is 0, we don't forward the message. That will essentially ensure that we perform a limited broadcast up to depth n in this network. So let's say we do a broadcast, let's say TTL is equal to 2. Suppose n is equal to 2, the initial TTL value is 2. So A is going to send it out, TTL will become 1 at B, and B is going to forward it and it becomes 0 at D. But so let's say that D has the file, or at least some file matching the keywords. So now how is A going to know about that? Okay, so what Nutella came up with, I mean there are various ways to do it, but what Nutella said is that we will not have the IP address of A in the query. We will just have a request for F. Okay, so the initial, let's say the first method used by Nutella. So the query had what we are searching for, F, and it had a unique ID. Let's call it a query ID. But it didn't contain the IP address of A. So later versions of course had the IP address of A, but we'll see how this might be useful. So suppose we had this, so there is a query for, let's say, F, and let's say there is some query ID, a unique ID for this, and this is going to forward that. Now D has, let's say, some information about about F which is being searched for. So B is going to cache this information. So it doesn't have F, but it caches the ID and whom it heard it from. Right, and so D also, let's say D has this, and it records who was the previous person it heard from. So D is going to reply this way to the previous peer, and it's going to say that I have such and such information, and it will give its IP address, and it will also give some port number. This is the application level, right, or the port number to identify the application. And this B is going to look up who was the previous person. So of course we'd have the QID also over here. And so B is going to look up who was the previous peer, and it will send out, it will just forward that reply. And let's say the IP of D and the port of D. Right? So can we do something a little bit more than this? So of course now A can download the information from D. Because it has the information about D and it knows that D has such and such information. Right? So in addition to this what I've shown over here, there will be some information about what exactly D has in relation to F. Maybe it will send a list of file names or something. Okay. So now what B can do is that B can also store some information about this. Right. So B caches, let's say there is also, in addition to this, there is also F. Right. So B can store the reply. And that might help because somebody in the future might also send a similar request for F through B, and B can directly reply instead of forwarding it to somebody else. Okay, so it can reply back with whatever information is stored over here. Okay, so that would enable a quicker search next time. So suppose next time, let's say there was another node here, let's say G, and G searches for F, then B can reply saying that D has this information. Okay, so whatever information D had sent in this first reply, it can send that information to G. Okay. So this was the first idea that they had. And of course, what if you didn't find it, you did a search up to 2 hops and you didn't find the information, then of course you could increase this TTL a little bit. So maybe you can start with TTL 1 and then you increase the TTL repeatedly till some maximum allowed TTL, and you see if you get the information that you want. Okay. So of course later versions of Nutella even put in the information about A in the query. You could give the IP address of A in the query itself so that D could directly contact A with that information. You wouldn't have to bother the people in between. Okay, but of course if D did that directly, then of course B wouldn't have the information that that D has this file and so on. Okay, so next time suppose G searches for the file, B would not have this reply information because the reply would have gone directly to A. Right? So anyway, so this is what Nutella did, and there were millions of people connected to Nutella and their network at the height. Right? So this is so let's say the second method. Query had the IP address of A as well. Okay, and we should say here, so you reply over the path which the query traversed. And here you reply directly to A. So why exactly do we need this QID? Well, suppose we have a more general graph than what is shown over here. The query might reach B or any other node through multiple paths. Right? It's going through this graph, and you don't want the same node to forward the same query repeatedly. Okay, so this unique QID helped that way, that you can prevent for any particular node from forwarding the same query multiple times. Okay, so it forwards it only once to its neighbors depending on the TTL. So there were various versions of Nutella, and just Let me give you some data I have here in my notes. So version 0.4 used a maximum TTL of 7, and version 0.6 used a TTL of 4. So why do we decrease the maximum TTL allowed? Well, it turns out that you have a very large network. As you know, when you initially have few networks, they may be sparsely connected. But when you have more and more nodes getting connected, the graph gets very dense. You may have some nodes which are very highly connected. So even 4 hops might actually result in the query going to thousands of nodes. And so if you have 7, you might actually end up querying millions of nodes. So that's going to be an overkill. That every time somebody wants to search for something, it goes to millions of nodes. Right? So they decrease this maximum TT. So this was the second generation. And of course, you might want to think, how is this good or bad? Well, of course, the good thing is that you don't have a centralized node. But the bad thing is that you have these broadcasts. Even if they are local, you could be sending to thousands of nodes, which is quite a big overhead. So suppose I have a dense network or any sort of network. Is there a clever way of trying to find out where the information is stored? Okay, so think about it here. What did we do? We did a broadcast of some kind, because we had absolutely no idea where to find the information. But can we do something more clever? So suppose there are n nodes, and I told you, so can you come up with a method to find out where the information is using just maybe by contacting only log n nodes? Okay, so this is the question that I want to put to you. If there are n nodes in the network, can I query only order of log n nodes to find where data is stored? So this is what people ended up doing, but what are we doing in Nutella? So, well, we might think, so suppose this TTL is fairly large, then pretty much we are going to end up querying order of n nodes, something like that. Like a big part of the network is going to be searched, and we find the information. Okay, but if there is only one node, let's say, which has the information, it seems like an overkill. That we are actually querying so many different nodes. So can we query a fewer set of nodes in order to find out where the information is? And clearly this limited broadcast sort of an idea doesn't work, because it's sort of a brute force method, and we are searching a large, you can say, part of the network, part of the graph. So how do we do that? How do we be clever in searching? So it's an intriguing idea, and the solution is also quite intriguing. How do we store information? So suppose there were some identifiers of nodes, and right now, of course, we have the IP addresses of various nodes. Let's say there is IP A, IP B, and so on. And then let's say these are the file names. Let's forget a moment about keywords and files and the differences and so on. Let's just say that we have a set of file names, well-known file names. Let's say there is F1, F2 and so on. Okay. Suppose there was a way of mapping these file names to these IP addresses. So we'll look at the exact solution, but suppose somebody wanted to search for F1. Suppose let's say node A wanted to search for F1. He had no idea where it is, and some random node actually has it, right? But let's say that we store information about where this F1 is stored at some other node. So let's say that IP, let's say there's IP Q, some node Q has this particular information. Suppose this has F1. Okay. And this is what we want to know, who has the information, so that we can actually download it from there. But can A identify some node to ask in some clever fashion? So suppose Q tells this node that I have F1. Okay. And suppose there is some mechanism by which A knows that if I have to find F1, then I should query E. So let's say A asks C, who has F1, and of course Q has done the initial work of telling E, because Q knows that other people are going to ask E about F1. Right, so Q tells E that I have F1, and maybe if somebody else also has F1, they will tell E. Right? So A, let's say magically, he sort of knows who I need to query to find out about F1, and so I will query E, and he gets information about, let's say, Q, and then A downloads it from Q. Okay. So we don't want this to be centralized. I mean, we could have a single node who acts like a server, like an Napster server, and everybody can update that node, right, and say what information it has and so on. But then we go back to a centralized solution, and then it has all the problems that Napster had. Okay. So we don't want to do that. So we want to be clever. We want it to be a distributed system. So let's say that this one, let's say IP Q has F1, but let's say there is an IP S, let's say, and this has F2. So can S store this information somewhere, but we don't want to store it in E, but somewhere else. Let's say it stores this information in B. So suppose S tells B, let's say it says I have F2, and magically let's say that if F wants to search for F2, node F wants to search for F2, suppose he knows that the person I need to contact is B, right? So it asks who has F2, and it gets a reply from B saying that node S has F2. So essentially what we need is some sort of a mapping. So we need to be able to map F2, in this case we are saying we are mapping F2 to B, right? And of course we said we are mapping F1 to E. So how are we going to do this sort of a mapping? Essentially, ideally you would want to choose a pseudo-random node. So you would map these files to appropriate nodes over here, and whoever, of course, everybody sort of knows this mapping scheme. So if he's looking for F, he would sort of know whom to ask. And whoever has those files also knows this mapping scheme, and they know that whoever wants that file will go to these particular nodes. So they themselves will use the same mapping schemes to identify these nodes and update them, and they will tell them that they have the files. Okay. So what sort of a mapping scheme to use? And one method is to use a hash function. So what is a hash function? Well, it takes an input. This is a hash function. It takes an input and this is a bit string of any length. And it spits out an output of another bit string but of fixed length. Okay, so it's mapping essentially your infinite space. You can have any bit string here, and it's sending it to this finite space over here of a certain set of bits. Let's say that you have a bit string of length m. Okay. And what we want is some sort of a random looking output. Okay, so you feed in some input here and you get something looking random over here. If you change even one bit in the input, you get something random. Okay, so the hash functions can do that for us. But the basic idea is you have an input of any length and you get a fixed length output. Okay, so you are mapping from this larger space into this smaller space. So what can we do? So you can feed in f1. Let's call this h. So you feed in f1 to the hash function and you get h of f1. You can feed in any f2, any function. Let's say you are searching for f2, you send it to this and you get h of f2 and so on. So these are deterministic, right? These functions are deterministic, a standard hash function. And we can use this for the mapping. Okay. So on the other side we have IP addresses. So how are we going to relate this to the IP addresses? So you might think, let's use a hash function which has 32-bit output, because suppose we are using IP version 4, we have 32-bit addresses. Okay, but one of the issues with that, and of course, suppose we do that, what would be the solution? Well, you just find whichever IP address, let's say here, is closest among all these, let's say, closest to this hash value, and let's choose that one. So let's say that IP E is closest to h of f1, and hence we choose node E. Okay, so that's one way to do it. But one of the problems with this is that the IP addresses of nodes in this network are not necessarily uniformly distributed over this space. So what may happen is that some nodes may end up doing too much of the work, right? So this hash function, these hash outputs for a well-designed hash function will pretty much be uniformly distributed over the space. Suppose we choose 32 bits, they will be uniformly distributed over their space, whereas these IP addresses are not uniformly distributed. right? So suppose this is the IP address space, right? So these hash values may sort of end up somewhere randomly over here, but there's no guarantee that the IP addresses are actually uniformly distributed. So let's say that let's say there is one node which is over here, and let's say there are lots of other IP addresses here. Then all the hash values which get mapped to this region, they are closest to this IP address. So this particular node will have to store information about lots of these files. Okay, so this is not necessarily a good idea. So what they said is, let's not just map these to the IP addresses directly. Let's take a hash of the IP addresses also. Okay, and so what we are going to do is that we do this, and we take a hash of the IP addresses and we plot them over here. So let me draw another circle over here. And let's say that this is going to 0 to 2 to the power of m minus 1, where m is the length of the hash output. So it doesn't have to be 32 bits. Okay, it can be anything, right? And now of course for different files you just send them through the hash function and you get, you know, various, let's say, hash values. Let's say this is hash of f1, this is the hash of f2, and so on, hash of f3. Essentially it gives you some pseudo random number over here. Okay. And now we take a hash also of the IP addresses. So let's say that hash of IP address of A comes over here, hash of IP address of B comes here, right? Or let's not put B over here. Let's say IP address of, let's say, C here, and we said that F2 we said is going to be stored in B. So let's say that hash of IP address of B ends up here, hash of IP address of E is here, and so on. Okay, and now we use our idea which we had earlier. So we are saying that whichever nodes, we are looking at this virtual space here, this space of m bits, and we are saying that hash of f1 is closest to this hash of IP address E. So what we are going to say is that this node, okay, is E, this is the closest, so E must store information about where F1 is stored. Okay. And similarly here, since B is closest to hash of IPB is closest to hash of F2, B must store where F2 is. B must let's say have information about where F2 is stored. Okay, so this is what we want. How to accomplish it, we'll have to figure out. That's where the log n is going to come in, because if everybody could immediately identify that that E is the node who has this information, then you could do a lookup in one step, right? So if A is searching for F1, he would directly be able to contact H of IPE. Okay, but A may not have that information, right? Unless he has IP addresses of all the nodes in the network or something like that, then he could of course do that. He could actually take the hash value of IP addresses of everyone and find out who is closest. But in practice, A may be connected to only a few peers. So what we are going to do is we are going to search a little bit, but we want to quickly find this node. We want to identify that indeed E is the node such that it is closest in this space to hash of F1. Right? So we'll have to do a search for that. But this is the idea. You map what you're searching for to this space using the hash function. You also map all the IP addresses to the same space. And what we need to do is we need to store, we need to record information about where files are stored in the appropriate node. So let's say that we said that in our first example that Q has F1. So Q must store in E, and it must say that I have F1, right? And A searches in E, it sends a message to E and it asks who has F1, right? And of course E is going to reply that Q has F1. So essentially this is the idea about how modern peer-to-peer systems work. Okay, it's a very clever system, and we'll see in a moment how exactly this is implemented in practice. So you have this abstract space in which you're embedding information in a clever way, so that if somebody wants information, he can very quickly zoom into the node which has that information. Okay? And once he finds that information, of course, he can download it directly from whoever has that file. Okay, so this is the clever idea, which is sort of the third generation of peer-to-peer systems. And all your BitTorrents and so on would use some sort of a system like this. Okay, so if you are using some peer-to-peer system to download movies, let's say, it would implement some idea like this. Of course, they do some things more advanced than what we will talk about. So BitTorrent will not download from a single node. It might download from multiple nodes simultaneously, okay, just to speed up the download. So there could be, let's say, not a single node, not just Q has that information, but there could be a Q1, Q2, Q3, 10 different nodes who have that file. And what BitTorrent does is it finds out the IP addresses of all those files, and then it will download parts of the file, different parts of the file from different ones of them, and it will put them together. Okay. So before that, we won't go into the details of BitTorrent and so on, but we will focus on how exactly to find out which node this is. So Q has to find out who E is, who is the node who is closest to this, because E may not be a peer whom Q is connected to. And A2 has to use a similar method to identify E, right? But if you are able to do that, then we can easily work this out, right? Other complications that will come in is, what if E leaves the network? Then we are in trouble, right? So because Q has told E that it has that information, and A was able to look up that information, but what if Q leaves the network? Then we are in soup. We are in a little bit of trouble, because the next node who is maybe closest to this particular value on this circle, the next closest node may not have that information. Q may not have stored that information there. So we have to make this method robust, right? So we will discuss about that next.